All right, everyone, we're going to get started here. Thank you for coming, first of all. My name is Brandon Boucher. I'm the Research Product Manager and Support Manager in ADM Instruments in North America. And I'm going to be teaching you guys a little bit about arithmetic today. If you're familiar with arithmetic, it's a really powerful tool. Essentially is the driver of all of the channel calculations and all of the different calculations that we do in LabChart. It really gives you a look under the hood as to how you can actually create your own calculations going forward in your data analysis. Before we sort of get started here, though, I'm going to talk a little bit about how the webinar is going to work and show you a few other things as well. Quickly, all of the audio from the attendees will be muted, so I won't be able to hear you. So if you want to get in touch with me, if you have any questions, please go to the GoToWebinar toolbar. There is a questions tab. And I'd like you to type any questions you have in there, please. And at the end of the presentation, I'll go back and read over those questions. And I will be sure to answer them as well as I can. Before we go into the next slide here, I'm going to go and switch over to my web browser. I just want to show you a few of the things we have coming up. If you like these webinars, you'll see that we have more webinars coming up here. These are, there's a few more coming up for our purposes as well for the LabChart Mastery. Those will be up on the website as we can get them. Where you want to go to find this information is adinstruments.com/events. We'll have many more webinars to come, so just come and look for those and find out more information about how you can attend those in the future. The other things we have here are workshops and training. Just want to let you know you have these coming up. If you like the webinars, the LabChart software courses that we have actually are very extended versions of these. They're 2-day courses. The next one is, starts tomorrow here in Colorado Springs. But we also have one in Boston, San Francisco coming up, as well as a few others. So if you want to look at those, please feel free to do so. And again, what you're going to get out of those courses is essentially, instead of just sitting through, an hour on arithmetic, we're going to take 2 days and we're going to go through as much of the software as we can get through in 2 days. We typically get through just about everything in the software. We try and tailor it as well as we can to the applications of the attendees and really make it, as hands-on and as custom as possible, so we can make sure that as we go through the 2 days, that everyone learns what they need to learn in the software to really be successful in their experiments going forward. So please look at those. It's adinstruments.com/events. So going back to my presentation here, just a bit of a disclaimer here as we're going through with the presentation. AD Instruments products, our manufactured products, are meant for teaching and research applications only. In saying that, they are not intended to be used as medical devices or in medical environments. Specifically, the products are not meant to diagnose, treat, or monitor a subject. That being said, some of our equipment in connecting those isolated front ends to power labs, some of those isolated front ends are suited for human use in research applications. We have some with a body protection signal, which means they're safe for being connected to humans, typically through the skin, so as long as there's no direct electrical connection to the heart. We also have some instruments with the CF protection symbol, which means they actually are suitable for direct connection to the heart in different experimental atmospheres. We manufacture everything under a quality management system. This is ISO 9001 and 2008. We have an accreditation body that actually comes in and certifies us under these standards. So that's something we're proud of and something we like to mention. So getting into our arithmetic here and what we're actually going to be seeing in this presentation. Arithmetic in LabChart for Windows is a channel calculation, and specifically, it's a channel calculation that drives all other calculations in LabChart. Any of the other calculations you're familiar with, whether it's cyclic measurements, the modules that we have, the scope spectrums, all of those different things that we have are really based in arithmetic. So the reason we like to talk about that is simply because we like you to know that arithmetic is more than just a math engine. It's an engine that drives everything that we do theoretically. If you had a way to do it. You could type in arithmetic the same results that you get out of those modules that you're using. You can get at arithmetic if you put them in there correctly. And what we're going to go through really is two different major features of arithmetic. First, we're going to do some basic calculations. We're going to show you how to do some of the things that we don't have built already for you and do some simple calculations. We're also going to show you how to use arithmetic to solve problems. And what we mean by that is we're going to use arithmetic to break down problems, approach them channel by channel, and issue by issue. And we're going to show you some really advanced ways that we've used arithmetic to break down a problem and solve a problem and calculate what we're trying to find in their data of interest. So the one way we often show people how to do that is using continuous online RMS. Now, when we talk about RMS, we've had people oftentimes ask us, if I'm interested in RMS, how do I do it? Because we don't have RMS built into our software. That being said, we do have RMS, in that you can do it in arithmetic. And so what we're going to try and show you here is how arithmetic and its syntax builds a normal function. You can see here I've shown you the function for RMS. And below that, what we have is an example of what we can use to copy that in arithmetic. So what we do first, obviously, we're going to be looking at the square root here. You can see we have the function squared. That's going to be noted by the channel of interest squared. Pretty simple. And that's going to be a caret 2 to note the squaring. If we go back here, the next bit we have here is the average. And it's an average of 1 second in this instance. And that's going to be the mean part of root mean squared. And then lastly, we have the square root on the outside, and that's going to be the square root. So that's SQRT that's shown there. So in getting at that, what we're trying to show is that we have the ability to do these types of calculations simply by typing them into arithmetic. And I'm going to show you a few ways you can figure out how to actually create these calculations on your own and what those look like. And hopefully we can get you started in the right direction and comfortable with creating these channel calculations in arithmetic. So going down, another feature that we like to use a lot in arithmetic is threshold and window. We like to show this first in PowerPoint presentation so it makes more sense. But using threshold and window, what we like to do is often isolate data that we're interested in. Ignore other data and isolate data that we're interested in. And one way we do that is just simply using a threshold. So you can see over here on the left, there's a threshold calculation. This is what this looks like. And we'll show you an example of it a little bit later on. But the threshold calculation will create a 0 while we are below the threshold. And we'll create a 1 while we're above the threshold. So if we say threshold, and we want to find the threshold of channel 1, and that threshold is A, the new channel calculation will give us 0 and 1, 1 being when we're above the threshold. Window is very similar, except we'll have 2 thresholds. Over here on the right, we have A and B. Between A and B, our new calculation will return a 1. And what that lets us do is really utilize LabChart to isolate those pieces of data that we're really interested in looking at. So we're going to show you an example of how this works as well. So I'm going to switch over to LabChart here. And we're going to show you a piece of data that we're going to analyze. We're actually going to do RMS together. So we should be able to switch over to that, and you should see this popping up shortly. So quickly, we're going to do, again, this RMS calculation. Now, what we want to do is we want to use the data that we have here in channel 1. What we're looking at is a diaphragmatic EMG. We're going to come back to this a little bit later because this is actually an arithmetic calculation as well. So we're going to show you how this was created from a diaphragmatic EMG. But what we want to do is we're going to show you the example of RMS. So what we're going to do here is we're going to click on the RMS channel, and then we're going to click on arithmetic. Okay, so again, we choose the channel that we want to place the calculation in, which is this RMS channel, and we're going to choose arithmetic. So right now, the arithmetic calculation is 0, but you can see here in this box, it's asking for your formula. In your formula, you have the ability to put in any sort of channel that you want, any function that you want, and they're all listed here. You have the channels, so you can say, I want to know channel, I want data from channel 5. You can see what gets placed in here is channel 5. Okay, so there's channel 5. We can say, I want channel 5 minus channel 1. We can type all types of things in here. Okay. What we're actually going to be getting out of this, though, in the end, is the ability to really create a more robust calculation than that. And then we can use these different functions to do that. So if we look at the function list, we have math, which is our addition, subtraction, multiplication. We also have trigonometry. We have logarithms, noise, different types of functions here. We have noise is just going to return random numbers. We have sign, which is going to return a positive 1 when our data is negative, and a negative 1 when our data is a positive 1 when our data is positive, and a negative 1 when our data is negative. We have absolute value. We have square root, pi, round, integer, mode, threshold, window, differentiate, integrals. We have all kinds of things here. Now, what I need to say about this list here is that it's not comprehensive. If you click on this Get Help dialog, and you click on arithmetic functions here, this is a place where you can actually get a long list of all the arithmetic functions, and not only a list of the arithmetic functions, but also how those functions are utilized to create our new calculations. So if we go find one here, for instance, we want to use, let's use differentiate. So differentiate x. X is going to be the source data. And this is width. We explain the width here different. We have diff order, which is explained here, in the fit order, which is explained here. So we have a large amount and flexible amount of information here that we can actually utilize to do these calculations. And this is all in the LabChart help menu. Gives you a good rundown on what we can do with this. Now, if I choose a function out of this list, say I want to choose threshold, you'll notice that threshold is here, and down below it tells us that my equation is invalid. If I hover my cursor over the red exclamation point here, it will tell you how to finish off your calculation. Okay, so it says threshold requires 2 parameters. You need x as the source, and then y, and if x is greater than y, and then we return 1. Okay, so that's the idea. It gives you an idea about how to create this. Now, one other thing I wanted to mention is, I put channel 5 in here again. The preview window here is going to show you what channel 5 is actually looking like. And if you do channel 5 divided by 20, whatever it is, or you do your own calculation, it's going to show you what that data is going to look like. And if we hit the play button down here, it's going to show you what it looks like in the future. As we record new data, what does that calculation look like? Okay, it's a great feature. Shows you the data that's coming in. Even though we're not recording data, it's showing me live what that data will look like when our calculation has been applied. And lastly, in the view here, we have the ability to choose what the display is, the scaling options. We also have the options to choose units. Okay, this is pretty important because the ability to choose units is going to give us, arithmetic is just simply taking in numbers and functions and spitting out the results. Arithmetic doesn't necessarily know what those results are supposed to be. For instance, if you're working with pressure units, or you're working with, in this case, we're working with millivolts. But on the back end of the calculation, arithmetic may not necessarily know, the result of this calculation is meant to be liters, right? It may not know, and so you need to just simply tell arithmetic on the back end what those results actually need to be. Okay, so something important here is just choosing units. Now, getting back to what we were trying to talk about here, we're going to use the data from channel 5, and we're going to do an RMS calculation pretty simply. Okay, so if you remember how that RMS calculation looked like, going back to our PowerPoint, the first thing we did was take the source data, in this case channel 5, and we're going to square it. So what we're going to do with that is we're going to say channel 5, we're going to put a caret, and we're going to put a 2. Okay, so channel 5 squared. Perfect. So now we have the square, part of root mean square. Now we're going to do a mean. And one of the functions we're going to use to do a mean is smoothsec. Okay, smoothsec does a triangular smoothing. It has 2 parameters, or 2 arguments. One argument, if we go down here to the, we'll do this here. One argument, if we go down here to the exclamation point, says there's one source. Okay, so the source is what data we want to smooth, and then the length is in seconds. So what we're going to do is we're going to say smoothsec ch5 squared, and then we're going to say, we'll make it 0.5 seconds. I don't know if that's quite correct or what that's going to look like, but it does give you a preview and shows you what that looks like. Okay, so this is my RMS of 0.5 seconds. Okay, so I may want to make this 1 second if I want to quantify that whole burst. We're going to do a smoothsec of 1 second, and then lastly, for the RMS, we're going to do SQRT. And we can finish that off, close the parentheses, and we have the root mean squared. We're going to click OK, and there is the RMS of our data. So that's it. That's the RMS. So pretty simple to do that. Now, we're going to show you a few other examples going through here and some other things, but we're going to come back to this because there's actually a pretty complicated arithmetic expression living in this file here as well. So let's look at another file here that we've created. We have in channel 1, 2, 3, and 4. This is a simple method of just simply showing how do we create a function generator using arithmetic. So in each of our channels, you can see we have an arithmetic expression set up. It says sine 25t. We have a triangular expression. We have a pulse expression. Okay, and again, all of these are listed in those arithmetic expressions. If we click Start here, this is what all of them look like. Okay, so this is a function generator. That's simply showing some more examples of what arithmetic can be used for. This is obviously not being recorded with my Power Lab. This is simply just being recorded with arithmetic, and those calculations are being placed over the top of those channels. Okay, so pretty simple. Again, we're simply just using arithmetic as a way to type in an expression. Now, the next thing we're going to show you is actually an example of how we're going to use arithmetic to solve problems. Okay, so what we have recorded here is simply a pulse transducer. Okay, some pulse transducer data. And that pulse transducer data has some artifact in it. This artifact, if we wanted to calculate something, say we wanted to calculate heart rate, and we go to cyclic measurements, and we try and calculate heart rate, you can see that that's going to cause us a problem. In these areas over here, you can see the heart rate 67, 68. That's great. But in that area where we have artifact, we obviously have an issue. And so what we can do is we can try and get rid of that data using arithmetic. So to do that, what I'm going to do is first say, I'm going to look at this and I'm going to ask myself, what's different about this data? Okay, what's different about this artifact data? Well, one thing that's different is that it goes outside of the range of normal data. Okay, my normal data lives in kind of this area here on the y-axis, and my arithmetic data is definitely going outside that range. Okay, so if you look at that, you can kind of see what I'm talking about. Now, what I'm going to do with that is I'm going to do arithmetic, and I'm going to try and isolate that data that goes outside of my range. So what I'm going to do first is I'm going to use a window calculation. Okay. If I close that parentheses and I look at the exclamation point, it's going to say window, it's going to ask for a source, and then it's going to ask for two thresholds. So what I'm going to do is I'm going to say window, channel 1. My first threshold is going to be the one on the bottom. I'm going to use about -50 for that. Now, -50 is not going to work. Okay, I'm actually going to use -0.5, and I'll explain why that is in a minute. The upper threshold is going to be 200, but in this case, actually, sorry, 0.05, and then I'm going to use 0.2. So what that looks like is, I need to make this a little bit larger. There we go. So I have -0.06 and 0.2 as my thresholds. The reason for that is because, and this is true for many features in LabChart, if you look at the units here are in millivolts. The units there are scalable units. Okay, LabChart looks at that unit, and it knows that the base unit is volt, and the milli part of millivolts is a scalar. So these values that I'm using here, -0.06 and 0.2, actually refer to -60 millivolts and 200 millivolts. Okay, but we're typing these numbers in as volts. And so that's an important lesson to learn if you're interested in using arithmetic going forward. Arithmetic knows the units you're interested, knows the units. If you have the units as millivolts or millisomething, it knows the base unit is the volt without the milli. So you have to put in your values here as volts. So that's why I have 0.06 and -0.06 and 0.2 as my values. So if I click OK here, you'll see I've isolated this. I have a 1 where all my good data is, and I have some zeros where my bad data is. Now, in looking at this, here's another question I have, and then that question is, if I wanted to use this now, this isn't going to give me a nice, clean profile. I'm still going to be left over with all of the data that's in between where it's going back and forth here. You can see it doesn't just go negative and doesn't just have one big artifact spike. What we have is a couple here. Okay, and so what I want to do is I want to turn this from one piece into another piece. I want to turn this from multiple ones and zeros into a single set of ones and zeros. So what I'm going to do here is I'm going to go to my second channel, and I'm actually going to go to arithmetic. And what I want to do with this now is I want to take this data and I want to smooth it out. So all of these zeros here contribute to one nice little waveform. So what I'm going to do with that is I'm going to use the function smoothSec. SmoothSec channel 2, and we're going to do that by about 0.3 seconds. And the result will be, and we can look at the preview window here, the result will be one nice little waveform here. See what that looks like. That's great. So now what I'm going to do, I guess one of the questions I get sometimes is, this is great that I have ones and zeros. I've isolated the bad data from the good data. Now, what can I do with that? How is that helpful for me, the ones and zeros? Well, the way that's helpful for you is now you can take these ones and zeros. What would happen if I multiplied this 1 and zeros by the original data. If I do that multiplication, what's left is the original data multiplied by 1, which is the original data, or the original data multiplied by 0, which is 0. Okay, so that's the value in doing this. Is you get a 1 that you can use to keep the nice, clean data, and you have a 0 that you can use to get rid of the bad data. So what I have here now after doing the smoothing is I have a little envelope here. And now I want to use this, so I have 1s, which is great, but I don't have 0s. So what I'm going to do here is I'm going to create one more threshold calculation. It's going to be right there at 1, which is going to leave me a nice little box that I can use. So in channel 4, I'm going to go to arithmetic, and I'm going to say, I'm going to use threshold. Channel 3, 1, and I get my box. Okay, I get 1 in where I have good data and a 0 where I have bad data. And last but not least, I'm going to multiply channel 4 times channel 1. And what I end up getting is the same data that's in channel 1, except during the artifact, I have a 0. Which is nice because now if I add another channel, I can very easily do that cyclic measurements calculation that I always wanted to do here, but instead of doing it with channel 1, I'm going to do it with channel 5, and now I no longer have that artifact in there, which is great. Okay. So a couple other things to note about this. You know, we have the 0 where we have the bad data, which is great. What would happen if instead of multiplying these two things, I divided them? So what if I wanted to say channel 1 divided by channel 4? Well, we get instead of a 0 in that section, instead of multiplying by 0, what I've done is I've divided by 0. And what I get is data that's undefined. The value in that is, in case I was interested in doing something other than a arithmetic, or other than a cyclic measurements calculation, what I would end up getting now is data that's undefined in that area. Say I wanted to know the mean. Well, LabChart, the mean of this area, would report an undefined number, which is the right way to do it. Instead of getting an artifact, you're going to be giving something that's excluded, something that you're not actually going to get data for, which is the right way to do many of those calculations. Okay? So there's an advantage to both sides, either multiplying or dividing. It's just a matter of, you know, how you're going to do your analysis and what you want the result to be. Now, one of the last things that we're going to show you here is in channel 6, what I'm going to do is I'm going to take all of these calculations. You see I did 4 calculations to get here. The nice thing about arithmetic, besides just being able to do a calculation like this in the first place, is that not only can I do a calculation like this, but I can do all 4 of these calculations. And I can take all of them and put them into a single calculation. So what I'm going to do here is in channel 6, I am going to do all of those calculations. I'm going to take channel 1, and the first thing we did was do a window calculation. Window, channel 1, we did negative 0.06 and 0.2. We did that. And now inside of the next calculation, or outside of the next calculation, I'm going to do another calculation. So I'm going to take this window calculation. I'm going to apply another calculation on top of it. The next thing we did was smooth sec of that 0.3. The next thing we did was threshold of that as a 1. And the next thing we did was multiply that by channel 1. So we get the same data. The difference is this, in one calculation, accomplished what we can accomplish in 4 calculations, which is a great thing. Okay. So the next thing that I'm going to do is I'm going to show a couple other examples here of how to use arithmetic to solve problems and do different calculations. One example is, this example data here, which somebody wanted to use to find alpha waves in an EEG. So if you look at this, what we did here was we have the raw EEG signal shown here in channel 1, and we have a number of steps. First, we have the raw EEG here in channel 1. Channel 2 shows alpha. What we did here was a digital filter. Okay, this digital filter takes the raw EEG, does a band pass, filters out everything except for the alpha waves, and that's what we got here, and you can pretty clearly see those. The next thing we did here was we did an integral, which integrated that area. We did a smoothing. Okay, we did a threshold calculation in arithmetic, and we created this. And then lastly, we did a derivative. Now, that's 1, 2, 3, 4, 5. And what we use this for here is we have a macro that goes through, finds the start and the end of all of these different waveforms. So here's the start, here's the end. Okay? And that's based on this final calculation here in the derivative channel. Now, one thing to note is all of these channels use things other than arithmetic. They use digital filters, they use integrals, they use digital filters. This one uses derivative. But one other thing to note here is if I add another channel, this same thing can be done in a single channel using arithmetic. You can see here that the original data is right here, channel 1. The first thing we did was here, we did a digital filter, or we did a band pass filter, which is right here. Next thing we did was integrate it, which is here. Okay. The next thing we did was a low-pass filter, which is here. Next thing we did is a threshold, and then lastly, we did the derivative. Pretty simple. I mean, so what we end up finding in here is that, you know, we have all these great calculations built into LabChart, but you know, if you want to do something really complicated, oftentimes you're going to end up creating a calculation that's 6, 7 channels deep in order to create the result that you want. Now, with arithmetic, you have the ability to take all those calculations and put them into a single calculation and get the same result, and that's really the value here that I'm trying to show with this example. So the last thing that we're going to do here is we're going to show you one more example of arithmetic and how it was used to solve a problem. This example was something that we put together not terribly long ago, and what we were trying to do was get rid of some artifact in this data here. And what I'm going to do is I'm going to show you just 2 channels of interest so it makes more sense. What we have here again is that same data that we were looking at before. It's a diaphragmatic EMG. Okay. The problem with the diaphragmatic EMG, and this is the raw data here in channel 1, is that what we have is a really bad ECG artifact. Okay. Using that, I mean, that ECG artifact is going to cause us some severe issues in trying to analyze this EMG data. If we try to do the RMS of this, we're going to get something that's a lot more of a mess than what we ended up getting when we first did this example earlier. And the result that we actually want is we want to get rid of that ECG waveform. So if you look down below here, that's what we have. Okay, and we did this with arithmetic. And we're going to show you how that was done. The first thing we did is we actually used a secondary ECG. We could have used the ECG waveform that's already in this channel. We used this secondary ECG to make it a little bit easier for us to get rid of those ECG artifacts. Now, if I go to arithmetic, I'm going to try to explain how this was done. The first thing we did here was we did a high-pass filter on channel 1. Okay, so let's see what that looks like. I'm going to copy and paste. So I'm going to do Control-C, and then I'm going to delete this. I'm going to show you what that looks like. So first we just did a high-pass filter on channel 1. And this is what that looks like. We simply did that high-pass filter so that we could get rid of, if you look at this right here, this is the T wave, and that's in the actual data as well. What we did is we got rid of that T wave, okay, using that high-pass filter. Okay, going back to our calculation, I put my other bits back in here. The other thing that we did was this. Okay, so let's take a look at that. What does that mean? Let's copy this first. What does this mean? The other thing that we did was we created zeros where there is an R wave. Okay? In order to create zeros where there's an R wave, the first thing that we did was we did a window of channel 2 between two values. So just like we did before with the pulse transducer thing that I showed you earlier, we did a window of this channel between X and Y, and every time I cross Y, we get a 1. Now what we did was a smooth sec, just simply that smooth sec and a threshold was simply to widen that area. Okay, that's all that was really meant to do, just like we did before. Remember, so just like we did before the pulse transducer, we essentially got a 0 and a 1, and then we widened it using smooth sec and threshold again. Okay, so that's the idea. Is we just simply create those zeros, we multiply it by the original channel, which had a high-pass filter applied to it, and then what we end up getting is this null EMG signal without the R wave artifacts. Now, there's one more bit of data here that we could use. Now, this is a small section of data, so I can't really use this. But we also took this arithmetic channel, which takes the R waves. You can see that this data, and let's go over here and kind of look at this data and see if we can see something with it. This data and this data are the same, except for it doesn't have these blank markers in there. We just wanted to see if we could do this. And so what we did was we took that original calculation that's here in channel 5, which is that null EMG, and we did more calculations on it. And what this actually does is it takes these little blank areas, finds where they are, grabs the data that's right next to them, copies it, and moves it over and puts it right on top of that 0. Okay? So we wanted to see if we had the ability to do that, and we did. So what we created was what looks like a continuous EMG. Okay? Now, you can debate whether or not that's good science, right? But you know, we really just wanted to see if we had the ability to do this. And we're copying a piece of hardware that's out there commercially available that produces this result right here, which is continuous and everything else. So we were trying to do the same thing as this piece of hardware. So what we ended up with is the ability to get rid of this ECG artifact and create this null EMG. So that's what I really wanted to show you here with arithmetic. Essentially, starting off with arithmetic, simply you should know that arithmetic is the basic engine that drives all the calculations in LabChart. You have the ability to create any calculations you want. It gives you the ability to look under the hood in LabChart and really drive your own calculations. We use arithmetic a lot to solve problems, break issues down, and create solutions like the one I'm showing you here that really creates a solution that's not built into our software, something that we wanted to define and an issue that we wanted to define and solve. And that's what we've done. So I hope that you guys found this information valuable. If you have any questions, feel free and call us here in 80 Instruments North America, and we can help you out as much as we can. And call your sales rep, and they can get you in touch with your support people, or call our main office, and we can help you out there as well. So that is the webinar. At the moment, I don't see any questions. If you guys have any questions, please feel free and type them into the questions tab. Otherwise, I want to thank you guys for coming, and I'll see you again next time.